Since the beginning of time, really, our ancestors have sat around their campfires and wondered those big questions that we all, tend to think about. Where do we come from? Why are we here? What else is out there? From here in Chile, we look up at the same sky, but due to the unique geography of this place, the skies are the most pristine and stable that you find on the planet. And so we have a great opportunity here. And we've learned a lot from studying things in Chile, but there's a lot left to learn. I'm Stuartt Corder. I'm Deputy Director of NSF Noir Lab. That's the National Science Foundation's nighttime optical infrared research laboratory. I'm also the mission scientist for AURA in Chile. You might know AURA as Observatorio Aura or even just Tololo, but through the course of the next few minutes, I hope to tell you and show you that we're a lot more than just Tololo today. My career has been spent launching new observatories, and I'm very proud to be able to be here today and talk to you about a new one that we have coming in the next year that is really going to change how we study astronomy. The questions that we have evolved a bit between before and now. We don't ask the questions quite in the same way. We ask the questions in more specific ways because we've learned a lot. So we ask sort of things like, what composes the universe? What is its structure? And we still want to know how we got here specifically, like the origin of ourselves. I'm not going to talk much about that today, but we'll talk a little bit more about the structure of the universe. What is it made of? And also, we've learned through time and studies that, it's not quite a safe space out there around us. There's a lot of things floating around, and many times in the history of the Earth, the universe has hit the biological version of the reset button, and we've had mass extinction events. So we know a lot more than we did before. But what keeps us from learning more, even so, is that the sky is just really too big to see and capture and see everything that's going on at one time. And the objects themselves are actually really faint. So that creates a really difficult challenge for astronomers, at least until now. So we hope to learn a lot more about dark matter and dark energy. In order to do this, we really need to study the structure of the universe as a function of its age. And honestly, thanks to the Big Bang, we can do that by studying the structure of the universe as a function of its distance, because due to the Big Bang, distance is equal to time. We also need to measure what's moving out there around us in order to really understand what threats there are to us, or maybe even what's going on in terms of the origin of the solar system and studying those objects that are out there. So we need to see what's moving, and we need to see the whole sky in a very deep and profound way. So again, need to make deep images. We need to see the whole sky, and we need to do it in a relatively quick manner. So how are we doing this? Well, 8 kilometers from Cerro Tololo, with the icon of early research astronomy, at least in Chile, is Cerro Pachón. That's the site of the Vera C. Rubin Observatory that will be inaugurated in the beginning of next year. The darks and stable skies from this region make really fine images. Now, in order to make a fine and deep image, we also need a big mirror. So the Vera Rubin Observatory has an 8-meter mirror, which is comparable to the largest research mirrors in existence today. Now, that doesn't do all of the things that I said before alone, because in order to see as much of the sky as possible, you need a very special design for your mirror. You need to be very flat, almost completely flat, in order to accept more of an angle on the sky. And so you need a unique design. And then you need a camera that can actually capture all of that information. But not only capture it, you need to be able to capture it, download it, send it off of the camera, and start a new image very quickly. So if you're going to do all of those things together, you need the site, which we have here in Chile, you need a big mirror, you need a special design, and you need a large camera. So the Vera Rubin has the largest camera ever built for astronomical purposes. And the idea is that it is going to visit the entire sky every 3 to 4 nights using this combination of telescope design, largest camera, and the pristine skies of northern Chile. So here you see Vera Rubin in the distance. This is the dome. The maintenance center is offset to the building. And this is actually pretty representative of how things look right now. The dome is almost complete, and we are on the verge of of actually starting on to full operations. We have a few things left to do and a few things left to test and verify, but we are on the road to launching this observatory, as many of you saw back on the 23rd of June with the first images that came off the Rubin telescope. So what all does this really mean? So we have a telescope, which you can see here moves very quickly, and that's also part of the game-changing nature of this telescope. So you're really going to have an opportunity for the first time to see the whole dynamic sky. We know by extrapolating from existing data on small patches of the sky sort of what we expect, but with a 10-year survey covering the entire night sky every 3 to 4 nights, we're basically going to make a video of the night sky. We're going to be able to see explosions that are out there. We're going to be able to see things that are moving within the solar system. We might even be able to see some things moving through our solar system from another solar system, be it rocks or comets or things that were ejected from other solar systems, and use that to study the difference between our solar system and others. So the agility really is the power here. So just to make so this is the Orion constellation that many of you you recognize from northern or southern hemisphere as one of the most prominent collections of stars on the sky. If Rubin can take an image of the entire Orion constellation in about 21 minutes, if you were going to do that with another telescope, with the second largest camera, let's say, which is actually located on Tololo right now, it would take you several nights to do this. So just to put that in perspective, Rubin, in terms of the depth and size of the images that it can get in order to make the full sky coverage as quickly as possible, will be 100 or hundreds of times faster than anything that's happened before. So you can imagine with this image of Orion, instead of taking 21 minutes to cover the rest of it down to the northern side, it would take nights, or 3 to 4 nights of observing on the sky would take years with the next best telescope. If you want to make a movie of the night sky, you don't want to make a movie that changes frame every couple of years. You want to make a movie that changes the frame every couple of nights. So what are we going to, what are we looking at with Rubin? What are the exciting things? Well, before our ancestors sitting around those fires, they saw a handful of things that moved around the sky and changed brightness with time. Those are the planets. They knew about those, and every now and then, maybe once every few hundred years, something really bright showed up and then disappeared, and they didn't understand what it was. So we're taking that dynamic sky image from those ancestral fires and making the same kind of leap that we've done with our understanding in other areas. So supernovae, explosions on the night sky, are stars that are taking material from around them and eventually become too big to support their own weight, and they collapse in one or another ways and explode. There are also stars out there that pulsate and make change their brightness because they're pulsating in time. The great thing about those targets is that they tell us about the distance to the objects, and that gives us that opportunity to study the structure of the universe with time. But in order to do that, you either need to see the explosions as they happen, and they only last in order to characterize them well, basically, you need to be observing them within a day or two to really get started. And for these stars that are pulsating, you need to know that they're there, and you need to measure them finely over time to measure their distance. And so with Rubin, again, with this video, you'll be able to study those distances and understand the structure of the universe as a function of time and as a function of age. The other thing we're going to do, as we saw briefly in the video they're going through, is we're going to see all the stuff that's moving through the solar system. Now, for those of you who tuned in to the first light images on the 23rd, you'll notice that in a few days, Rubin found 4,000 asteroids, 2,000 of those which were new. So that is really, gaining a much deeper understanding of what's out there in the solar system. And in fact, right now, there's an interstellar asteroid visiting us from another system, and we're studying that with the existing telescopes. Rubin is going to be able to find probably a few of those a year, rather than just finding our third one now in about 8 or 10 years, which should allow us to do a lot deeper study of those sort of visiting objects, and also allow us to protect ourselves in case we find an asteroid that might happen to wish us ill, shall we say. Okay, so in order to do all this, Rubin is great, but it can't do it alone. So the Rubin telescope is going to find all of these things with its scanning pattern going around the sky, but it's just going to keep scanning. In order to really understand in detail where these things are going, study their composition, learn about their properties as they evolve as a function of time. You need a network of telescopes. Now, one of the craziest things about Rubin, in my opinion, is that in full operation, it is going to see about 10 million changes in brightness or position on the sky every night. Now, we don't have enough telescopes in the rest of the world and people to study it to actually go through all of those and figure out which ones are interesting and which ones aren't. So a lot of really detailed software has been developed, including by folks here in Chile, to help filter out and categorize those changes to help the field of astronomers understand, is this an interesting change that I want to look at, or is this something that's not really in my field of study? And of course, something may be interesting to one person and not interesting to another. So Rubin will discover this 10 million change set of objects on the sky every night. It will go to an archive. Those changes will be noticed by differencing the images. Then alerts will be sent out. Again, millions and millions a night. And then through these complicated sets of algorithms, which use machine learning and artificial intelligence, we'll be able to sort through which of those things are interesting to some people and which are interesting to others. And then on top of that, you'll be able to trigger observations on other observatories to continue following that specific object that you might be interested in while Rubin continues to scan the sky. We at Noir Lab basically have set ourselves up to do this. So on Pachon, where Rubin is also Gemini South, which is an infrared optimized telescope of 8 meters, and SOAR, which is a 4-meter telescope, ideally using the optical. And then we have Tololo with the 4-meter Blanco telescope sitting just a few kilometers away. So we have a system, as sort of highlighted here, where you can trigger, based on the Rubin outcomes, observations on our other telescopes. You don't have to tell us where you want to look beforehand or when. You just need to tell us what kind of thing you want to look at. And when your alert is triggered and you find that thing, you can say, I want Gemini to go look at this right now. And it can run off on the left side of this image and take a light fingerprint of the source, maybe to study its composition or its temperature. And on the other hand, you might want to just follow the object and measure how its light changes with time. Well, SOAR on the right-hand side could be following that evolution. And so you get information and you put it together, the detection, the change, the fingerprint, the time evolution of the source, and put it into a much deeper understanding of that object that may have exploded at the bottom. So thank you very much for your time today. We have the Rubin Observatory should be starting its 10-year survey coming up in the next, I would say 6 to 9 months is our target. And with that, we really will begin this 10-year study of the discovery and study of the nighttime dynamic sky. Thank you.